Chapter 30, Electromagnetic Oscillations and Alternating Current. It covers LC oscillations, damped oscillations in an RLC circuit, alternating current, forced oscillations, power in alternating current circuits, transformer. You can find them in the timeline. LC oscillators, new physics, old mathematics. In this chapter, you will see how the electric charge Q varies with time in a circuit made up of an inductor L, a capacitor C, and a resistor R. From another point of view, we shall discuss how energy shuttles back and forth between the magnetic field of the inductor and the electric field of the capacitor, being gradually dissipated while these oscillations continue as thermal energy in the resistor. We have discussed oscillations before in another context. In mechanics, we saw how displacement x varies with time in a mechanic oscillating system made up of a block of mass m and a spring of spring constant k, and a viscous or frictional element such as oil. The latter figure shows such a system. You also saw how energy shuttled back and forth between kinetic energy of the oscillation mass and the potential energy of the spring, being gradually dissipated while the oscillations continue as thermal energy. The parallel between these two idealized systems is exact, and the controlling differential equations are identical. Thus, there's no new mathematics to be learned. We can simply change the symbols and give our full attention to the physics of the situation. LC oscillations, quantitatively. Of the three circuit elements, resistors R, capacitance C, and inductance L. We have so far discussed the series combination RC and RL. In these two kinds of circuit, we find that the charge, current, and the potential difference grow and decay exponentially. The time scale of the growth or decay is given by a time constant τ, which is either capacitive or inductive. We now examine the remaining two element circuits combination, LC. You will see that in this case, the charge, current, and potential difference do not decay exponentially with time, but vary simultaneously with period t and angular frequency omega. The circuit is said to oscillate, and the resulting oscillations of the capacitor's elementary field and the inductor's magnetic field are said to be electromagnetic oscillations. Now we look at this picture. We start from here, where the capacitor is fully charged with positive on the top, negative on the bottom, and no current in swing. In this case, the capacitor has the maximum energy. We know the unit volume electric field has half Q squared over C energy, and magnetic field in the coil per unit is half Li squared. In this case, I equals 0. Q is the maximum, so we have electric energy stored in this capacity. Total energy is concentrated here. And then what happened? What happened is the positive charge will go this way, okay? And we see we have a current, okay? And in this case, the charge is reduced, so we see the electric energy reduced and the magnetic field energy increase until the current reached the maximum. In this case, whole energy of the system concentrate on coil, magnetic field. So I is maximum. And in this case, no charge on both plane, so Q is 0, UE is 0. And then, because of inductance L, the continuum will not stop or continue, but gradually reduce. And so the positive accumulate on the bottom plate and negative accumulate on the upper top plate of the capacitor. And we will see that electric field energy increase and magnetic field decrease until the L equal to 0. And this is the maximum whole energy stored in the capacitor. We go back like this situation. Different is that charge now is moved to bottom. And we have the same process up, go back to this one. This is circulation, okay? And we know that one, the potential difference between the coil is minus L di dt. And the potential difference across the capacitor is Q over C. They are equal. So this one minus this one equal to 0. And then we know I is dq dt. So we put I equal to dq dt, we get L move here, we get second derivative of Q with that respect to time t equal to plus Q over LC equal to 0. This is the second differential equation, which we call a constant and linear. We saw it before, okay? This is the potential difference across the capacity of the circuit, okay? As a function of time t, because the Vc equal to Q over C. Q changes, so Vc changes. Is auto, and this is VR. The potential is proportional to the R, okay? So actually, this is Q, this is Q situation. This is I situation. We can measure Vc and VR, and we find the Q and R situation, okay? Example, a 1.5 microfarad capacitor is charged to 57 volt. The charging battery is that disconnected, and a 12 millihenry coil is connected in series with the capacitor, so the LC oscillator occurs. What is the maximum current in the coil? Assume that the circuit contains no resistance. Now we saw from energy conservation, okay, when this is a 57 volt, all energy is here, okay, and when all the energy moves to this one, we get maximum current. This is what we have to find, the maximum current. Okay. This is the energy stored in the magnetic field in the coil, and this is the energy stored in the capacity. This is the maximum, and this is the maximum we move. Okay, maximum. So what is maximum? This 57, this coil is 1.5 microfarad. We have L, we can find I. This is a trivius, okay, it's trivius. In an actual LC circuit, the oscillations will not continue indefinitely because there's always some resistance present that will drain energy from electric and magnetic fields and dissipate it as thermal energy. The circuit may become warmer. The oscillations, once started, will die away, as the figure suggests. You see, will die away, okay? Compare this figure with the right one, which shows decay of mechanical oscillation caused by frictional damping in a block spring system. This is our system, LC system. This is a mechanical system. They are more or less the same. Okay, the magnitude decay. Okay, it is possible to sustain the electromagnetic oscillation if we arrange to supply automatically and periodically enough energy from outside source to compensate for that dissipated as thermal energy. The electrical mechanical analogy. Half x squared is the potential energy of spring, is equivalent to half 1 over CQ squared, the electric energy in the capacitor. Half mv squared is similar to half Li squared. Here we see dx dt equal to v. Okay, dx dt. dq dt equal to I, so that's why they're similar. Okay, q corresponds to x, 1 over c corresponds to k. I corresponds to v, and L corresponds to m. We know in the mechanics oscillation, the omega equal to square root k over m. So k equal to 1 over c, m corresponds to L. So in electrical oscillation, the omega is equal to 1 over LC square root. LC oscillations quantitatively. The block spring oscillation, U equal to U mass, U spring. This is the kinetic energy of the block, this is potential energy of the spring. They are constant. Okay. Suppose we no resistance, no friction. And then, so du dt equal to 0. We do this one, that's mv dv dt, half cancel, kx dx dt, it should be 0. And we found v is dx dt, okay, dx dt. So in this case, v is dx dt, so this is a second derivative of x with respect to t. And this is equal to 0, that we don't have to care that dx dt. So what we get second derivative of x respect to time t plus kx over m. This is a second differential equation, linear. We know the omega equal to k, omega squared equal to k over m. And the answer is x equal to xm cosine omega t plus phi. And xm and phi depend the initial condition. Now, we go back to LC oscillator. Same reason, okay. This is for coil, magnetic field. This is called electric field in the capacitor. They are constant, okay. So with the du dt equal to 0, here you get half and it cancel out L I di dt. This is what half just cancel out. You get q what c dq dt, okay, q dt, and I is dq dt. So di dt is second derivative of q with respect to time t, okay. dq dt, the second derivative, q over c dq dt equal to 0. And from this equation, we get second derivative q related to time t equal to q minus q of c, or plus 1 over LQ equal to 0. And from this equation, we know omega squared equal to 1 over LC. Okay, and the q is some q cosine sine, okay. It's sinusoidal, simple harmonic motion, okay. And this is a qm, and phi depends on the initial condition, okay. And omega squared equal to 1 over LC. And this initial condition is equal to Q0 and I0. I0 is dq dt 0. This is our answer. We see the energy of electric field is Q squared over 2C. And Q is Qm cosine omega t plus phi. Okay, right? And this magnetic field is concentrated in the inductor. It's half I squared. I is dq dt. Okay. Now we do the dq dt. We find minus omega. Okay, so we have minus omega q and sine. Okay, and then we do get this answer. This omega square q square, so to see. And we see omega plus L is 1 over c. This is a 1 over c. So this is a q squared over c sine this one. This is sine. Okay? And then we plot them. This is energy E, electric field. This is energy B, magnetic field. Okay? We plot them. We see the blue line is UE. The green line is magnetic field. We see that at any time the sun is a constant. It's constant, okay? And they all oscillate. Sample. For the situation described in the above sample, let the coil induced be connected to the charged capacitor at time t equal to 0. The result is an LC circuit like that in the first figure. And this is what, okay? And C is given 1.5 microfarad. L is given 0.012 Henry. And at the beginning, VC is 57 volt. Question A, what is the potential difference VL across the inductor as a function of time t? Now, from this one, we know that the inductor and capacitor connect in parallel. So their voltage across is the same. So VL equal to VC. And what is the VC? VC equal to Q over C by definition. What is the Q? We don't know. We know which is equal to Q cosine omega t plus phi. Okay. Now let's see the condition. As given, okay, T equal to 0. This is a maximum voltage, also maximum Q. So Q0 equal to big Q, the maximum Q. And we put this one here, T equal to 0. So we find phi equal to 0. And phi equal to 0, this is Q over C cosine omega t. And Q over C is VC, okay, the maximum cosine omega t. We found a VC, we found omega, we get the answer. Okay. Okay. And VC equal to Q over C is 57. Okay. Yeah. Now, the big VC is 57. Omega is 1 over square root LC. We have L, we have C, we find omega. So we put this omega and the VC inside, we get our answer. VL, function time, 57 cosine 7,100 t. Question B. What is the maximum rate, dIdt maximum, at which the current I changes in the circuit? We know this one, C, L, and VC. And we know this answer, phi equal to 0. Okay. Now, dIdt maximum is we want to find. First, we find the dIdt. dIdt is the second derivative of Q with respect to time t. And we bought this one, we get minus omega squared Q cosine omega t. Phi is 0, we have proved before. Okay, so we look at the sine cosine, the maximum is omega squared Q. What is omega? Omega is 1 over LC. Q is VCC. A C cancelled out. Okay, so we get a VC over L cosine. The maximum is VC over L. VC is 57, L is given, so we get the maximum change rate. 4,800 amperes per second. Damped oscillations in an RLC circuit. Damped oscillations in an RLC circuit. Now we connect a resistor between them. If a resistor R is present in the LC circuit. The total electromagnetic energy U is no longer constant, but decreases with time as it is transferred steadily to thermal energy in the resistor. So, total U. This is total U. They are not constant. Okay? We say du dt. The energy reduced should be consumed in R. It's I squared R. This is minus number because they reduce. Okay? And we put this one inside. We do the derivative. 2 half cancel Li di dt. 2.5 cancel out. Okay. Q over C dA dq dt equal to minus square R. And we know I equals to dq dt. We put this one inside. So L divided here. This dq dt I cancel out. 1I. So we get here's one's dq dt. L. This is the second derivative of Q with respect time to T. dq dt equal to I. So you put i's here, and this one, I, we can cancel one I on both sides. We get di dt equals L second derivative of Q with respect to time T. Plus, you see this R moved here. R I dq dt plus cancel this Q over C equal to 0. What is this? This is a little bit familiar. This is a second order differential equation. It's linear, no square, linear, okay? And we got to solve this differential equation, get the answer. You may not get into this subject in mathematics than I do in my way. We know that first we assume the solution, Q. Without this resistance, it is sine cosine. With this resistance, we know that the Q is deteriorate with time T. We assume we have this term, E minus AT. And the T is 0, this is what? This beginning. When a T goes into infinity, this is 0. As we expect, Q will be 0. Okay. This A, I don't know. I can find it out. Okay. So here we have Q E minus AT cosine omega C. Phi and Q are two constants. That depends on the initial condition. Q or dq dt is I. Now, we do the derivative, dq dt. You have two terms. The first term you have minus A E minus AQ cosine. The second term is the Q E minus A is the cosine. This is minus sine omega. This is omega minus sine. Okay? And then this is dq dt. We know to do it again. The second derivative with respect to time t. We do this two terms. Okay? The first term is you have minus again. So Q minus positive. QA squared cosine. Second is you have cosine, you have a minus sine omega. Minus positive. Sine omega. Omega, you have omega. Right? Yeah. And look at this one. This first derivative is minus A. So you get the minus positive. Positive QA omega. Sine. And then you do this sine. Sine is cosine, you have omega. Omega squared minus Q omega squared. That's right. So you have this four term. Now what do you do? We try to go this way. We multiply 1 over C to Q. Look at this one. We multiply I to dq dt. We get this one. Okay, two term. And we multiply L to d dt. It is 4 term. And we then put them together. This L, the second derivative of Q respect to time t, plus R, first derivative dq dt, plus Q over C, this is equal to 0. Now, this must be 0. We see a lot of cosine sine, and we get the cosine together, sine together. I'm not going to do it. Let's see this one. E minus t cosine term, we have Q over C, okay? And the cosine, this one, we have minus RQA, minus QRA, this cosine. Okay. We have LQA squared cosine. And this one, we have minus LQ omega squared. This is a coefficient in front of this term. And then we have sine. Look at the sine. Minus Q omega R. And this side, they are the same. So 2QA omega L, what is L? Equal to. Now, look at this answer. This equation should be equal at any time. So T can be a large number. They should always equal to 0. So what we can get? We can guess the only chance is the coefficient in front of this is 0, right? Okay. So we put them together. You get an answer. Only chance we can have answer is the coefficient in front of these complicated stuff is 0. So we get LQA squared minus LQ omega squared minus QRA plus Q equal to 0. Okay, and 2QAL minus RQL equal to 0. Okay, now, what I get? In this one, okay, Q omega cancel out. We get A. A equal to R over 2L. We put A equal to R to L, we find omega. Okay, the omega equal to square root 1 over L C plus C. Now, we get the answer because we have A, okay, we have omega, right? And this one is originally omega squared, okay? You have one more term because you have R. Without R, without this term, we get omega 0, right? So finally, answer is Q equal to Q, this one, okay? Q equal to this one. And this one, A is minus R over 2L. This omega is this one, okay? And you have a Q at 5. These two constants are determined by initial conditions. Now, we have the original way to get this physics way. Assume one more term, we get the answer. Now, we get the answer. Because of this loss of energy, the oscillation looks like this one. As T approach to infinity, this term equal to 0, Q equal to 0. Because of this loss of energy, the oscillations of charge current and the potential difference continuously decrease in amplitude, and the oscillations are said to be damped. As you will see, they are damped in exactly the same way as those of the damped block spring oscillator in mechanics.
This series circuit of a capacitor bank, a resistor, and an inductor will be used to demonstrate damped oscillations in an LRC circuit. The voltage across the capacitors is shown by the vertical position of the trace on this oscilloscope. When the switch is thrown to the left, a battery charges the capacitor bank. Throwing the switch to the right connects the charged capacitor in series with the resistor and inductor, with the resulting oscillations in capacitor voltage shown on the oscilloscope. If we increase the capacitance, the period of the oscillations increases. What will happen to the oscillations if we increase the resistance in the circuit? The oscillations die away more quickly as the resistance is increased.
Sample. A series RLC circuit has inductance L 12 millihenry, capacitance C 1.5 microfarad, and the resistance R 1.5 ohm. Question A. At what time t will the amplitude of the charge oscillations in the circuit be 50% of its initial value? When Q, the answer, write it down. The question is, what time t? Okay, the amplitude is original half. Original what? T equal to 0, this equal to 1 is Q. In other words, what time the amplitude is half Q. Okay, in other words, this is equal to half. We take the log, we can get the t. This is minus c log half, cancel out, so this t equal to log 2 or 2x. See, we put on the right side, we get an answer. Only 0.011 second, 11 millisecond. Question B. How many oscillations are completed within this time? We have time. Once we know the period, we can find this answer, right? Okay, what is the period? Let's see. First, we find omega. In this case, we put number I, put air, we find R over 2R is much smaller than 1 over LC squared. Okay, so we drop this one. This is physics. Approximately is okay. So the omega 0 is equal to 1 over LC. We put the air, we put the C, we get omega. Okay, once you get omega, we get the time t. Omega t equal to 2 pi. So t equal to 2 pi over omega. We get the t. Once we get the t, we know how many cycles because we already find that this t is 30 and this t is 13. In 13 circle, it drops to half. Alternating current. The oscillations in an RLC circuit were not damped out if an external electromotive force devices supplies enough energy to make up for the energy dissipated at thermal energy in the resistance R. Circuits in homes, offices, and factories, including countless RLC circuits, receive such energy from local power companies. In most countries, the energy is supplied via oscillating electromotive forces and current. The current is said to be an alternating current, or AC for short. The non-oscillating current from a battery is said to be a direct current, or DC. These oscillating electromotive forces and currents vary simultaneously with time. The basic advantage of alternating current is this. 1. As the current alternates, so does the magnetic field that surrounds the conductor. This makes possible the use of Faraday's law of induction, which, among other things, means that we can step up, increase, or step down, decrease the magnitude of an alternating potential difference at will, using a device called a transformer, as you will see later in this chapter. 2. Moreover, alternating current is more readily adaptable to rotating machinery such as generators and motors than is non-alternating direct current. 3. Alternating current are central not only to power distribution system, but also to radio, television, satellite communication system, computer system, etc. 4. Finally, we know that for many devices, such as light bulbs and toasters, the direction of the motion is unimportant as long as the electrons to move so as to transfer energy to the devices via collisions with atoms in the device. The basic mechanism of an alternating current generator is a conducting loop rotated in an external magnetic field. Now, this is a loop. This is a constant magnetic field. Okay, we have two kind of slip ring. This is when they have the metal brush contact with them. Okay, in practice, the alternating electromotive force induced in the coil of many turns of wire is made accessible by means of slip ring. Is rotate with them. Okay. Attached to the rotational loop, each ring connects to one end of the loop's wire and electrically connected by a conducting brush. Okay. Again, which it slips to the rest of the generator circuit. AC generator, we have this electromotive force equal to E maximum sine omega d t. Omega d is the angular speed of the loop in rotation. Okay. We know epsilon E equal to minus d phi dt. The d phi dt, the flux, so this loop. And this phi equal to b dot a. The a is the area, is rotate, the direction a changes, rotate, and magnitude is the same. B is a constant. So this b dot a equal to ba cosine omega t. And we do the derivative with respect to time t, we get minus sine omega, ba sine omega t. You have minus, 2 minus, you get positive. So epsilon equal to ba omega sine theta. And the ba omega, we call the epsilon maximum sine omega t. This is an AC generator. Forced oscillations. One studied the charge potential difference and the current in both undamped LC circuits and damped RLC circuits with small enough R oscillate at a regular frequency omega equals 1 over square root LC. Such oscillations are said to be free oscillations, free of any external electromotive force. And the angular frequency omega is said to be the circuit's natural angular frequency. When the external alternating electromotive force is connected to a RLC circuit, the oscillations of charge, potential difference, and current are said to be driven oscillations or forced oscillations. Now, you have this one. This is a driven oscillation. Whatever the natural angular frequency omega of a circuit may be, forced oscillation of charge, current, and a potential difference in the circuit always occur at the given angular frequency omega drive, omega d. At any time, this is a circuit, we have IR, IC, IL, they are the same because they connect in a series. Second, VR plus VC plus VL, equal to epsilon. And epsilon is given epsilon maximum sine omega dt. This is a driven frequency. Then there is a current flow in the circuit. This current we saw equal to Im sine omega t minus phi. This is our given. Our job is, we know these things, we want to find I. What is it? You have Im and phi. Notice that here in the book, textbook, the definition here is minus sign, okay? So what we found is I maximum and phase difference, okay? This is our job, to find Im and phi. Three simple circuits. Let's see the simple circuits first, then we put them together. This is a circuit. A single lobe circuit containing a resistor, a capacitor, and an inductor. A generator represented by a sine wave in a circle, okay, produces an alternating electromotive force that establishes an alternating current. The direction of the electromotive force and the current are indicated here by only one instant. Even they change direction and change magnitude. This is only one in moment instant. Now we see that this simple thing. A resistive load, only one resistor. And we know this VR equal to epsilon. And epsilon can express as Em sine omega dt. And VR can express in other ways. This is magnitude and omega t. Okay? So we combine these two. Okay? In 1 second, suppose this is minus, there's a positive epsilon, and then we have VR equal to Em. Okay? So VR equal to Em. And IR equal to VR over R. This is alternating. Okay? And VR equal to epsilon M sine. So IR equal to VR over R sine M. And we can write this one as Im sine omega t minus 0. What this means is, in our case, is we need two things, I and phi. In this case, Im is VR over R. VR over R. Phi equal to 0. Okay? And so we put as VR and IR. This is IR. This is VR. They are in phase, no phase different. Okay. If we plot, say, VR and IR alternating current and alternating voltage, they are in phase at 0 at the same time, maximum at the same time. Okay. The time varying quantities VR and IR can also be represented geometrically by phasors. We have learned the phasors before. Recall that phasors are vectors that rotate around an origin. Okay? Counterclockwise as a positive. Okay? And VR and IR is their projection on the vertical axis. Okay? This is their magnitude. Okay? This rotates with this angle velocity omega d. Now this angle is omega dt. Okay? And the project on the vertical is their alternating current, IR and VR. Okay? So the VR equal to VR sine omega t. IR equal to IR sine omega t. Okay? Such phasors have the following properties. This phasor have properties. Angular speed, this angular speed. Both phasors rotate counterclockwise about the origin with an angular speed equal to angular frequency omega d. Okay, this is with the finish, this is a positive. It can rotate clockwise, then this is minus number. Okay. So this positive is anti-clockwise. The length of each phasor represents the amplitude of the alternating quantities. VR for the voltage and IR for the current. Projection. The projection of each phasor on the vertical axis represents the value of alternating quantity at time t. And this is the VR is this one, object this one. And IR is this one, product of these vectors. Rotation angle, this angle. The rotation angle of each phasor is equal to the phase of the alternating quantity at time t. The voltage and current are in phase for resistor. So their phasor have the same phase omega 0t and the same rotation angle, and thus they rotate together. This is for resistor. Okay. VR equal to VR sine omega t. IR equal to IR sine. So they are in phase. They rotate together. Sample. Pure resistive load. In the figure, resistance R is 200 ohm. And the sinusoidal alternating electromotive force device operates at amplitude EM 36.0 volt and the frequency 60.0 hertz. Question A. What is the potential difference VKR across resistance as a function of time t? And what is the amplitude VR of VR? Now, it almost gives you everything. We know that one. This VR equal to epsilon. We can express VR as VR sine omega t. It's equal to electromotive force E. And this electromotive force you can express EM sine omega t. You compare these two. Okay? You compare these two. This one is 60.0 hertz. Omega is 2 pi f. So 2 pi f. And we put those inside. This is 36.0. This is 1 pi. This is the V. So we compare to this one, we have a VR equal to 36.0 volt. So VR equals EM equal 36.0 volt. Question B. What are the currents IR in the resistance and the amplitude IR of IR? Now we write it down. IR equal to V of R. We know VR 36.0. We know R 200. We got IR. Okay. Every run-down system, alternating current IR equal to IR magnitude sine omega t. That's phi for resistance only is 0. Okay, so we can write it down. IR equal to I sine omega d. We know omega. We know IR, so we get an expression for this one. Okay. So we know the IR, the big IR is 0.180. This one. Second one we discussed, very simple, a capacitive load, only capacitive, without resistance and coil. We know the VC equal to epsilon. And VC we could express VC sine omega t. Okay, because epsilon is this way. Okay. And this VC equal to epsilon m. And we see the Q. The Q is equal to CV. There's alternating changes. Okay, it changes, this changes. Okay, you put CV, VC equal to VC sine omega t. What is I? The I is dQc dt. We do the derivative with respect to time t, we get omega d CVC cosine omega t. Now, from this expression, we can see this. We can write the standard. Standard is ICM sine omega t minus phi. When we write this one, we find IC in this case, magnitude is omega d CVC. And the phi is minus 90. Now, here I want to emphasize, you compare the IC and VC. IC is ahead 90 degrees, then VC. IC is leading, okay? Now, here, let's do some exercise. We set XC equal to 1 over omega C. We call this one the capacitive reactance. And we rewrite IC equal to VC over XC. This is 1 over C. This will look like I equal to V over R in direct current, right? Easy to recap. You have to remember this one. If you plot in the time, then we can say VC equal to IC XC. We plot one, we see current in capacitive load. Current is leading 90 degrees. By then definition, the phi is minus 90. Remember, don't confuse it, okay? Anyway, capacitive current leading 90 degrees, okay? And the phi is minus 90. And we put this one, we find, okay, with the V. V is sine, cosine. And I is leading. So V is 0, the I is already 90 degrees, it's already top, okay? This is the one. Now we see this one, VCIC. VCIC. VC, IC equal to VC over XC, right? And this is minus 90, okay? Current is leading voltage. Phi is negative 90 degrees, okay? We express in phasor. We see this is the VC, EC. And current is ahead. When you stand here, you will see the I first when you rotate here. Then after 90 degrees, you see the V. This is in advance. So this is direction, 90 degrees is IC, okay? And their project of this one is their current component, okay? And they rotate together with frequency omega. Now, IC equal to VC over XC. XC, by definition, is 1 over omega C, okay? In capacitor, the current is 90 degrees ahead of the voltage. Current is 90 degrees ahead of voltage. They rotate together. Is ahead because you look here, you see this one, then see this one. Sample. Pure capacitive load. In the figure, capacitance C is 15.0 microfarad, this one. And the sinusoidal alternating electron motive force device operates at amplitude E maximum 36.0 volt and the frequency FD 60.0 hertz. Question A. What are the potential difference VC across capacity and the amplitude big VC over VC? We know VC, we can write this one, VC sine equal to epsilon. And epsilon can write E maximum sine 2 pi FDT. Okay, we know this is 36.0. We know this is 60.0 hertz. So we can write VC. And the amplitude, big VC, is 30.6. Right. Question B. What are the currents in the circuit as a function of time, and the amplitude IC of the alternating ICT. This is routine. We write it standard. Okay, the standard. We want to find this and this. This is given. Okay, 60.0 times 2 pi, 120. Okay. Now what we do? Okay, we know this phi c is minus 90 degree, minus half pound. So we get this one. And we find IC. How we find IC? IC equal to VC over X. The XC is 1 over omega C D. Okay. And VC is 36.0. So we find IC. We put this in, we get the answer. We get the answer. Okay. 0.203 sine 120 pi t plus half r. Okay. This is the answer. Last, an inductive load, only an inductor coil. We know VL equal to VL sine omega t, the standard right, the magnitude, angular frequency. Okay. And we see this one, suppose in 1 second, this is a positive, this is negative from this one. And you have current go this way, and then we know the induced electromotive force for this air is minus air di dt. Now, the magnitude is air d dt. This is positive, this is negative from the Lenz's law. Okay. So we rewrite it, forget this one. Okay, this is positive, negative. Okay. This one is in this standard. Okay, this lower than this one. Okay, so we find UL equal to air d air dt. They are equal. Now from this, I got DIL. DIL equal to V sine C, okay, times dt over L. Okay. And we do the integration. This integration, this constant, we're gonna, so this is sine omega dt, omega dt dt, okay? So this integration is minus cosine omega t divided by omega d. Very simple integration. You do the derivative, you get cosine derivative become minus sine, minus positive. And you have omega t cancel on this one, you get VL of L, right? Yeah. And then this one, we will write in a standard form as I sine, and cosine omega t, we can write as minus sine omega t minus 90, minus positive. In this way, it is standard form. What is standard form? The ice air is this one. Phi is this one. So in this case, inductive law, we see IC in the VL over XTL, okay, and phi is 90. And we set the X air equal to omega air. We call it inductive reactance. And then we found VL equal to IL XL, like Ohm's law. Okay. Now we plot it, you see, in this inductive, the current is lag behind 90 degree. Okay. Now, this is voltage. Okay. And the current is here. Okay. And current is negative 90 degree. This is 0, negative 90 degree. Okay. All right. We can express this one in phasor. Okay. VL is VL sine omega t. IL is IL sine omega t minus x. We put this one. This is a V. VL. I is 90-degree lag. If you stand here, you see this voltage first, then after 90 degree, you see I. Okay, and both of them have angle 90 degree. They rotate with the same angular frequency omega d. Okay, right? Yeah. And we know IL is the VL over XL. XL equal to omega L. Okay, that's the way we look at as in phasor diagram. They both rotate with angular frequency omega d. Keep the angle is 90 degree. Current is 90 degree lag behind. In inductor, the current is 90 degree lag behind the voltage. Sample, pure inductive load. In the figure, inductance L is 230 millihenry, and a sinusoidal alternating electromotive force device operates at amplitude EM 36.0 volt and a frequency FT 60.0 Hertz. Question A. What are the potential difference VL across inductance and amplitude big VL? Now we write it up. VL we can write in this search, and this equal to epsilon, and epsilon equal to epsilon maximum sine omega t. We compare these two, we get a VL. Okay, this is 36.0 per C. So we can find the VL equal to 36.0. Question B. What are the current IL in the circuit as a function of time and the amplitude IL of alternating IL? XL by definition we set equal to omega L. We know omega, we know L. Look at XL. And what is IL equal to? VL over XL. VL is 36, XL 86.0. We get IL. Okay, and this is inductance. So current lag behind 90 degree. Phi is 90. So IL equal to IL sine minus phi. This is phi is 90 degree. Okay, half pi. So we put them together, we get everything. IL 0.4 volts sine omega t. Epsilon equal to epsilon m sine omega t. This is driving electromotive force. Okay, it's given. I is Im sine omega t. That's our definition. This is minus phi. Our job is find Im and phi. If a pure R, phi equal to 0. Pure C, this is minus 90. Pure left, this is 90 degree. Okay, so for pure R, I are equal to epsilon m over R. No phase different. For pure C, I C equal to xm over xc. The phi is minus 90, so because positive 90, the current is ahead of voltage. Okay. For the pure inductance, XL equal to omega L. Okay, this is 90 degree, phi is 90 degree. The current is 90 degree lag behind voltage. Okay. I only remember one, this current. Current for capacitor current ahead of voltage, 90 degree. So in the case, we take phi is minus 90. Xc is set 1 over omega c. XL equal to omega L. IRM equal to VR over R. IC equal to Vc of Xc, or epsilon m X, Xc equal to omega 1 over omega L. For pure inductance, equal to VL of XL, XL equal to omega L. This is the one. Summarize. This is in phase. This is current leading voltage. This is current voltage leading current. The series RLC circuit. Resistor R, capacitor C, and the inductor L connect in series at this external electromotive force. At any time, because the current is alternating, so this is only one instant, okay? We can change direction either. At any time, the current pass through all these three elements are the same. That means IR equal to IC equal to IL equal to total I around this circuit. And potential difference of resistors plus capacitor plus inductor is equal to epsilon. Okay? The external electromotive force E epsilon equal to epsilon m sine omega dt is given. Our job is to find the current in this circuit. We define the current as Im sine omega t dt minus phi. Why is it minus? No reason, because our textbooks do it that way. So in order to you convenient to understand, I use the minus phi. Our job is find I. This is given as omega d. So what the job is find Im and phi. Now let's start. From above study, we know that for a resistor, current and voltage are in phase. For a capacitor, current is 90 degrees ahead of voltage. In inductor, the current is 90 degrees behind the voltage. Okay. And we know IR equal to IC equal to IL. This is our study point. So we should try to find the current amplitude at any arbitrary time t. First, we assume this I equal to I sine omega dt minus phi. We want to find I in theta. And we know this I is the same for resistor, capacitor, and inductor. This is I. This is I. This angle is omega dt minus phi. Okay, now we started. We use this equation. IR equal to IC equal to IA. Then we construct VR, VC, VL. This is VR, VC, VL. How? Now, this is the direction of I. VR is in phase, okay? And VC, IC is 90 degrees ahead of VC, so this is VC. And IC is 90 degrees lag behind the VL. That situation. We see VC and VL always in the line, okay? They are 180 degree phase different. All right? Okay. Then we know VR equal to IR. VC equal to IXC equal to I over omega C. And VL is IXL, I omega L. And we do it. Then we use this equation. Okay? This equation. You see, the total V equal to the sum of the three. Okay? The epsilon equal to sum of three. This is the same line, so this is called a VL over VC and VR. So V epsilon is the vector sum of these two. Okay? Now we now see this one. This is I. Okay? This is I. Okay? This should be omega t. Why? Because this is omega t minus t is I direction. And this must be phi. Right? Yeah, must be phi. This is I. This is phi. Okay. So the omega, the epsilon is omega t minus phi plus phi omega t. Okay? And then we notice that VCL and VC itself can larger than epsilon because this is smaller than E, but this is the difference, so they can be larger than E. Finally, we want to find I and phi. How? We look at this picture. We see this square equal to VR square plus VL just C square, right? Yeah. And then we see VR is IR, VL is IXL, VC is IXC. And we put number inside. I take the I square out, is R square XL minus XC parallel square. And we put number inside. That's equal to, we call this one, the blue one, the Z square. We define Z square, we call it impedance, Z. The definition of Z is square root R square plus XL minus XC square, square root. And we put the number inside. Okay. XL is omega L. XC is 1 over omega C. Okay. And then we found this one. Okay. The current amplitude epsilon. This current is equal to what? Equal to epsilon Z over Z. Z is this one. So we find the I. We know everything here. Yeah, this is I. Or next, we want to find the phi. Now, we look at this triangle. We want to find phi. We see the tangent of phi equal to this one, VL minus VC over VR. Okay, and this direction is the current direction because VR is to I at the same phase. So tangent of phi equal to VL over VC. We know VL equal to IXL. VC is IXC. VI is IXR. So we can this one we can cancel out I. We get tangent of phi equal to XL minus XC over R. We know everything this one, so we can know the phi. The phi is arctangent XL minus XC over R. Now let's study the I. The I is E over Z. Okay. We have two special cases in the case. The first case is R XL equal to 0. That means you have only capacitor. We don't have inductor and resistance. And you put here, you find out this is a pure capacitive circuit. Okay. And we look at this one. Yeah, look at this one. XL is 0. This is 0. So the infinity. Tangent phi, and you have a minus sign here. So this phi is minus 90 degrees. Okay, minus 90. The second case is XC R0. That means you have only pure inductor. Okay, in this case, this is 0. This is 0. So tangent phi equal to positive infinity, and the phi is 90 degrees, as we know before. Okay, that capacitive circuit phi equal to minus 90. The conductive circuit phi equals positive 90. Let's look at this picture. This circuit I is leading E, so this is capacitive. Okay, we look this one. How we look this one? We suppose this two waves go direction from right to left. In this case, you see this one. The I will reach this first. E will reach this second. So I leading E. Conductive. This one is I lag behind the E. You look this one, okay, the E get this first and I second, so I is lag behind. This is inductive curve, okay. If this is only resistors, then they are in phase. The pure resistive. The current that we have been describing in this section is a steady state current that occurs after the alternating electromotive force has been applied for some time. When the electromotive force is first applied to a circuit, a brief transient current occurs. Its duration before settling down into the steady state current is determined by the time constants tau equals L over R and tau equals RC as the inductive and capacitive elements turn on. This transient current can be large and can, for example, destroy a motor on starting up if it is not properly taken into account in the motor's circuit design. Resonance. The oscillation will reach its maximum when omega d equal to omega 0, which we call the resonance condition. That means the drive frequency equal to the original frequency. This is the drive frequency omega d. This is I. We write I equal to epsilon m over R squared plus omega L minus 1 over omega c squared. And when XL equal to XC, this is XL, this is XC. In other words, this XL minus equal to 0. So this is 0, then we get IM. This 0 means what? This means omega d equal to 1 over LC. This is a frequency, original angular frequency. In this case, this is 0, so Im equal to maximum epsilon over R. In this case, VL equal to VC. They can be much larger than E, but the minus, they cancel out. Resonance. This is a plot, okay. This is omega d equal to omega equal to 1, that's equal. This is pure resistive. Okay. And this is this area, XL large XC. This area, XC large LL. We see that's when at frequency omega d equal to omega 0, the I is maximum. Of course, different R value, you get a different value of I. Okay. In turning the turning knob, we are adjusting the natural frequency omega 0 of an internal LC circuit to match the frequency of the broadcasting state. There's a counterpart of resonance phenomena in mechanics.
We'll use this LRC circuit board to demonstrate electrical resonance. An inductor, resistor, capacitor bank, and AC power source are hooked together in the configuration shown on the front of the board. The voltage and current for each component can be displayed on an oscilloscope using this probe. The value of the inductor can be changed to bring the circuit's natural frequency close to the driving frequency. This causes the circuit to resonate, and a strong current flows. Here are the voltage and current across the capacitor bank as the circuit passes through resonance. Here are the voltage and current across the resistor. We'll use this LRC circuit board to demonstrate electrical resonance. An inductor, resistor, capacitor bank, and AC power source are hooked together in the configuration shown on the front of the board. The voltage and current for each component can be displayed on an oscilloscope using this probe. The value of the inductor can be changed to bring the circuit's natural frequency close to the driving frequency. This causes the circuit to resonate, and a strong current flows. Here are the voltage and current across the capacitor bank as the circuit passes through resonance.
Current is leading 90 degrees than the voltage.
Here are the voltage and current across the resistor.
They are in phase.
Here are the voltage and current across the inductor.
The current is lagged behind the voltage, 90 degrees.
Here are the voltage and current at the power supply as the circuit passes through resonance.
Sample. Let R 200 ohm, C 15.0 microfarad, L equal to 230 millihenry, F equal to 6.0 hertz, and epsilon equal to 36.0. These parameters are those used in above samples. So we already calculate XC equal to 86.7, XL equal to 177. XC is 1 over omega C. XL is omega L. Question A. What is the current amplitude I? It's very simple. We have to find the Z first. Definition: Z equal to R squared plus XL minus XC squared. You put a number inside, we get the Z. Once we have Z, we have the I. EM over Z. Very simple to get this one. It's 0.164 ampere. Question B. What is the phase constant phi of the current in a circuit relative to the driving electromotive force? This is phi. Arctangent phi equal to XL over XC of L. So we put the number inside, we get a phi. Okay. This phi is minus 0.422 radians, minus 24.3 degrees. That means the current leads the driving electromotive force. Okay. Then we put the I. This is 0.164. This is minus 0.424. Plus minus get a positive. The I is leading the magnetic force outside. So this circuit is capacitive. Or in some cases we have a parallel circuit, not a series. Okay, what we do this one, I'll give you some basically. In this parallel, we know this is called a circuit 1, this is circuit 2. The voltage in this 2N is equal to the voltage this 2N. The I is equal to I1 plus I2. So what we do is we take the electromotive force E as a reference, because on both circuits they are the same. Okay, and this is 2, the circuit. This is a inductance, so the current lag behind E with phi L. And this circuit 1, the current is leading E. So we have this this phi C, and we take this E at the same. We combine the I1, I2, we get the I. That's the principle. Power in alternating current circuits. In RLC circuits of the figure, the source of the energy is the alternating current generator. Some of the energy that is provided is stored in the electric field in the capacitor. Some is stored in the magnetic field in the inductor. And some is dissipated as thermal energy in the resistor. In steady state operation, which we assume the average energy stored in the capacitor and inductor remains constant. The net transfer of energy is thus from the generator to the resistor, where the electromagnetic energy is dissipated as thermal energy. So P equal to I squared R. We put the number inside. Okay. Now, this is the changes as time changes because sign changes. What we want, because they change very fast, we write it I squared R sine squared. This is the change all the time. What we really concern is the average rate over time at which power is transferred to the resistor. So we want to average it. And we know that when we put the sign and the sine square, this is a 1, this is a 1. So the average sum square is over half. We know that sine square plus cosine square equal to 1. So their average is 1. And the sine square average is equal to cosine square average. So each of them, the average half. And we put half inside here. So we got the P average is half I squared this. Okay, it's average. And this is not enough. We rewrite it. We write it I over square root square T. They are the same. Okay, they are the same. This is blue one equal to the red one. Okay? And the quantity I over square root, we call it root mean square or root mean square, value of the current I. What is when, how you find it? Now, first you square I. Then you take the average, this is I. You square I. You average over the period, okay? And then you take square root. So you call it root mean square. What you do is you square first. You take a mean, then you take the root, okay? So this definition is the I over square root 2. So in this case, the P average is I root mean square average R. Okay. Alternating current instruments such as amperemeter and voltmeter are usually calibrated to read root mean square values. And I root mean square equal to I over square 2. And V root mean square equal to V over square root 2. And E root mean square equal to epsilon over square root 2. Okay? So we have I root mean square equal to E root mean square over Z. Okay? This is our new definition. Power effect cosine phi. This is a special in alternating current because the voltage and current are not in phase in general. The P average is I root mean square square R. And I root mean square equal to epsilon root mean square over Z. You take one I out. And we do operation Z over here. So rewrite it as epsilon root MSC, I root MSC R over Z. We know in DC circuit, the power equal to EI. And we similar in alternating current, the P power average equal to epsilon root mean square dot I root mean square. Okay, and effect called R over Z. You look at this one. Look at the equation. Okay, this is VI. R, VR is IR. Z is equal to I. Epsilon is IZ. So R over Z is cosine phi. The phi is the angle between the current and voltage. So we define the cosine phi equal to R over Z. And then, what is R over Z? We do operation. We multiply by I on both sides. What it is? This is called VR, and this is epsilon VC. Epsilon, okay? Look at this one. This is the VR. This is epsilon C. So in this one, this over this is cosine phi. And we rewrite this one called E average is epsilon root mean square times I root mean square times cosine phi. That's cosine phi. The phi actually is the angle between the E and I. This is special in alternating current. To maximum the rate at which the energy is supplied to a resistor load in an RLC circuit, we should keep the power factor cosine phi as close to unit as possible. This is equivalent to keep the phase constant phi in the above equation as close to 0 as possible. Phi equal to 0, cosine 0 is close to 1. Okay. If, for example, the circuit is highly inductive, it can be made less so by adding capacitance to the circuit, thus reducing the phase constant and increasing the power factor in the equation. Power companies place capacitors throughout their transmission system to do this one. Okay, what we want to be larger, so we can deliver the energy from factory to the consumer. Example: a series RMC circuit driven with epsilon R1 S equal to 120 volt at a frequency FD 60.0 Hz contains a resistance R 200 ohm, inductance XL 80.0 and capacitance with XC 150 ohm. Question A: what are the power factors cosine phi and phase constant phi of the circuit? Now we just will find first one, find the Z, because we have a definition. That's very easy. R XL XC, and then we find cosine phi. Cosine phi defined as R over Z. We know R over Z, you get cosine phi. Okay, and we know this one. This one. This one is smaller than 0. Okay, that means cosine phi is smaller than 0. Okay, yeah. So phi could cosine phi. We get minus number. Why is minus number? We judge from here. Okay, just from here. Okay, and XL is smaller than XC, so this conductive. Okay, that's why phi must be smaller than 0. Only from this one you can have two answers. We pick one is minus because it is conductive. XC larger than XL. Question B: what is the average rate P average at which energy is dissipated in the resistance? Then we see the average equal E epsilon root mean square times I root mean square cosine phi. We put everything inside. Okay, put everything inside. Okay. This I equal to epsilon over Z. Okay, we put everything inside. You get the answer. Question C: what new capacitance C new is needed to maximize P average if the other parameter of the circuit are not changed? That means we will have to change the C. So make it is maximum I. What is when? Okay, when XC equal to XL, then P average, P maximum. We want to maximize it, we'll make XC equal to XL. We know XL. Okay, so we can find the C new. C new is okay, XL minus 1. 8. So you get a C. Energy transmission requirements. To satisfy a given power requirement, we have a range of choices from a relatively large current I and a relatively small voltage V to just the reverse, small I, large V, provided only that the product IV is required. So we need transformer. Transformers. In electric power distribution system, it is desirable for reasons of safety and for efficient equipment design to deal with relatively low voltages at both generating end, the electric power plant, and the receiving end, the home or factory. Nobody wants an electric toaster or a child's electric train to operate at, say, 10 kilovolt. On the other hand, in the transmission of the electric energy from the generating plant to the customer, we want the lowest practical current, hence the largest practical voltage, to minimize I2R losses, often called ohmic losses, in the transmission line. This is a transformer. We have primary coil and a secondary coil. This is an electromotive force. This is a V primary and this is a V secondary. And this round turn is N turn, NP turn, and this is NS turn. This transformer is such a device that can, as design considerations require, raise or lower the potential difference in a circuit, keeping the product current times voltage essentially constant. It has no moving part, operation by Faraday's law of induction, and has no simple direct current counterpart. The ideal transformer. The ideal transformer in the figure consists of two coils with different numbers of turns, wound around an iron core. The coils are insulated from the core. In use, the primary winding of NP turns is connected to an alternating current generator whose electromotive force given by epsilon equal to epsilon m sine omega t. And the voltage from the second coil, Vs, equal to V primary times Ns of Np. Because each turn they induce the same electromotive force. And if Ns is larger than Np, then we call it step-up transformer. The voltage Vs is larger than Vp. If Ns is smaller than Np, this is smaller than 1, we call it step-down transformer. An ideal transformer, 1. No resistance of the primary and secondary windings. No resistance, no disappear. Magnetic hysteresis losses in the core are negligible. When S is open, there's no current. Is equal to 0. And this can see that each turn the electromotive force induced is minus d phi by dt. So the Vp is equal to Np E turn. Vs is Ns epsilon turn. We divided Vp or Vs and we find Vs equal Ns or Np Vp. When switch S is on, the situation is different. You have Is flow in the second law, and Is squared R equal to Vs squared over R. Is induces its own alternating magnetic flux in the core, and this flux induces an opposing electromotive force in the primary windings. Vp, however, cannot change in response to this opposing electromotive force because it must always equal to the electromotive force that is provided by the generator. 4. To assume 3, a new alternating current IP must appear in the primary circuit. Its magnitude and phase constant being just that needed to cancel out the opposing electromotive force generated in the primary winding by Is. So we have the power conservation, energy conservation, IPVP equal to ISVS. That's conservation of energy. And then we also have Vs equal to Ns over NPVP. And so Vp equal to Np over Ns Vs. According to this formula, we get I. The Is equal to Ip Np over S reverse equation, and Ip equal to Is Ns over Pv. We divided Vp over Ip. We know Vp over Ip is Rp. This is R equivalent from the plenary point of view. Okay, and we do this one V. So this is Np over S squared, Vs over Is. Vs over Is is Rs. Okay, yeah, is the loading resistance. So we have in the primary circuit, R equivalent equal to Np over Ns squared R. This R equivalent is the value of the load resistance as seen by the generator. You see, you apply the tree. What do you see? You see the E equivalent here, Vp. Okay, so the E equivalent is what he say. Forget about this one. Okay, so actually, what he say, this is equivalent. This Vp over Rp equal to Ip. Impedance matching. For maximum transfer of energy from electromotive devices to a resistant load, the resistance of the electromotive force device and the resistance of the load must be equal. We have learned in before. The same relation holds for AC circuits, except that the impedance, rather than just the resistance of the generator, must match to that of the load. This one, we want match the impedance of the generator, okay? And resistance usually is not this number, so we can use the transformer to match them. Okay. It often happens as when we wish to connect a speaker set to an amplifier that its condition is far from met. The amplifier and the speaker set being of high and a low impedance, respectively. We can match the impedance of the two devices by coupling them through a transformer with a suitable turns ratio, Np over Ns. I don't know whether you have impedance. When you want to use your earphone connect to the speaker, you didn't get a sound at all because it's not matched.
These wire coils and an iron core will be used to show how transformers can raise or lower the voltage of alternating current. We'll start with these two identical coils of 500 turns on the iron core and put 70 volts AC on the first coil with a light bulb hooked up to each coil. The two light bulbs are equally bright. The voltage on each coil is therefore about the same. Let's replace the second coil with a 250 turn coil. how bright will the bulb be on this coil? The bulb is much dimmer on this coil, since the output voltage of the coil is only about 35 volts. If we turn the transformer around so that the 70-volt input goes into the 250-turn coil, the bulb on the 500-turn coil is much brighter due to the 140-volt output of the coil. Finally, we'll place this 10,000-turn coil on the iron core to show the high voltage developed due to the large number of turns.
This wire coil has many turns centered on an iron core extending above the coil. Flipping this switch allows alternating current to run through the coil. A second coil is connected to a standard household light bulb. When we lower this second coil over the iron core of the first coil, the bulb lights. Notice that the brightness increases as the second coil approaches the first, and decreases as it moves farther away. This third coil has many fewer turns and is connected to a bulb that needs a much lower current to light. Lowering this coil over the iron core lights the bulb.
Sample. A transformer on the unit pole operates at the V primary 6.5 kilovolt on the primary side and supplies electric energy to a number of nearby houses at VS 120 volt. Both quantities being root mean square values. Assume an ideal step-down transformer, a purely resistive load, and a power factor of unit. Question A. What is the turns ratio NP over NS of the transformer? We know NP over S proportional VP over VS. We know VP 8.5 kilo. We know VS 1200 volts. So the ratio is easy to find out. Okay, 71. Question B. The average rate of energy consumption or dissipation in the houses served by the transformer is 78 kilowatt. What are the root mean square currents in the primary and the secondary of the transformer? We know IP equal to P over VP. We know VP, we know power is 75. So IP, we know it's on, okay? This is supply to the house, okay? And we know IP, we also can find IS, okay? Because VS is 120, okay? Question C. What is the resistive load RS in the secondary circuit? What is the corresponding resistance of RP in the primary circuit? RS is VS over IS. We put 1200 over 60, we get 0.18 ohm. Okay? And RP equal to VP over IP. VP is 8.5 thousandths volt divided by IP equal to C. Or we can find IP in different way. Okay? This R equivalent equal to NP over SPR. We put this ratio, we get the same answer, 930. Next chapter, chapter 31, Maxwell equations, magnetism of matter. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021. based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.